Hello again, ladies and gentlemen. Mr. Johnny here, looking to go over some chapter 7.3 through 5, trends on the periodic table. All right, so before we look at the problems, let's just talk about the trends. All right, here we got the trend for atomic radius, and it is a little bit counterintuitive until you know why there's this pattern. So you would think that it should get bigger as you go left or right because the atomic numbers are going up, right? You go 7, 8, 9, 10. They're getting more massive, but counterintuitively, they're actually getting smaller. And here's why. So we got to remember something about the arrangement of the periodic table. Everything in the same period has the same principal energy levels, the same number of energy levels, right? Same number of layers. So as we start left, we have a positive charge in the nucleus. We have an energy level surrounding it. As we go left to right, what we're doing is we're making that nuclear charge greater. We're adding more protons, so the charge of the nucleus is getting a lot more positive. We're also adding more electrons, which are negative. So what's going to happen as we increase the nuclear charge? Well, that's going to have a stronger pull on the electrons. It's going to pull them closer to the nucleus. That's how you think of it. All right, well, now that the nucleus is more positive and I got more negative electrons whizzing around it, it's going to be like two magnets. You got a weak magnet on the left, and then as you go to the right, you get an even stronger magnet, and it's pulling everything closer, which is why it gets smaller to the right. Kind of counterintuitive, but that's, once you understand that what's going on with the charge interactions, then it makes a lot of sense. Well, why does it get bigger as we go down? Well, that's kind of simple. As we go down, we're adding a whole nother energy level to our atom, which is going to get it bigger. And just like layers on an onion or a cake, more pleasantly, cakes have layers, right? So atomic radius does that. All right, so now if we look at electronegativity, it does the exact opposite. All right, the greatest electronegativity is up towards the top right. All right, so well, why does that happen? Well, let's think about what electronegativity is. It's, an attraction to electrons in a bond specifically. So, well, why would the top right have the strongest attraction? Again, it's the same deal, right? I gotta stop pressing that button. So as we go left to right, we're increasing that nuclear charge, which is gonna have a stronger attraction towards the negative electron. So it makes sense that going left to right, it should actually increase. All right. Same thing with top to bottom. If we were to add a whole nother layer to an atom, you're adding pretty much insulation between the electrons and the nucleus. You're adding shielding, right? There's more shielding going on, so it's in the way, which means it's going to have a weaker attraction for electrons, right? And tell me I put two of the same thing. Oh well. All right. Ionization energy does the same thing. Ionize. I can't spell. All right. So ionization energy being the amount of energy needed to remove an electron, makes sense that the thing that's holding on to electrons the most requires the most energy to remove an electron. So let's take a look at some of these problems. So it says 8. The atomic radius of main group elements generally increases down a group because, all right, well, for this one, effective nuclear charge increases going down a group. That's true, but that's not why it would get bigger. If anything, oh wait, it's not A. Effective nuclear charge, keyword there being effective, doesn't really increase going down a group. Effective nuclear charge decreases going down a group. That's, not really what has to do with why as you go down a group it gets bigger. It has to do with the number of principal energy levels, principal quantum number. Right? So the more energy levels you get, the bigger it is. 9. Which of the following gives the correct order of atomic radius for Mg, Na, P, Si, and Ar? So you can just use the pattern. Where is the biggest? The biggest is towards the left and towards the bottom, right? Now, sometimes they'll give you things where it doesn't follow this pattern. Like, well, what if I had you know, an element here, and then I was looking at an element over here. Well, all right, cool. That doesn't have as many energy levels on it, but this one has a stronger pull for the electrons because of that nuclear charge. So which one is it? When you're given problems like that, just look them up. Just look up what each thing is, right? And you find your answer should be choice D, as in David, right? So bigger ones are towards the left, so choice D. All right, number 10. Which of the following atoms has the largest radius? Again, you got to remember the radius is the biggest to the left and towards the bottom. All right, so which one of these things has the biggest one? Again, this is one of those weird ones where it's like, oh, well, which one is it? I don't know. I don't know. In that kind of instance, just look them up. Just go to your table S for your Regents reference tables and look them up with your eyes. Right? Look them up. You do that and you find your answer should be C for sulfur. All right, 11. Which of the following is an isoelectronic series? New vocab word. Well, if we just break it down, iso means same, and electronic means electrons. So we're looking for the same number of electrons. Well, which group here has the same number of electrons? Well, let's take a look. Oxygen, I know, has 6, and how did it get this -2? Added 2, so it has 8. Fluorine had 7, how did it get this -1? You added 1 to it, so it has 8. Neon, noble gas, has 8. Sodium should be 281, right? Should have 11. Oh man, I'm sorry, I was talking about valence electrons, but it's still true, right? But instead of 8, it's actually 10 total. And same with fluorine, it had 9, you added 1, so it has 10 total. Neon is 2-8, so it has 10 total. Sodium is 2-8-1. How did it get that positive charge? It lost that last electron, so it has a total of 10. All right, E is the only option where all of them have the same number of electrons in total. 12. Which isoelectronic series is correctly arranged in order of increasing radius? So we're looking at the same number of electrons. So we have the same configuration, but we're talking about size. So let's think about this. The only thing that's different is the nuclear charge, right? So the ones with the lower atomic number have a smaller nuclear charge than the ones with a greater atomic number. So the one that's going to be the smallest is going to be the one with the greatest atomic number. All right, well, which one of these things obeys that rule? D, by my calculations. D, smallest one is going to be the one with the greatest nuclear charge, in this case, calcium. And the biggest one is going to be the one with the smallest nuclear charge, chlorine. 13. Of the following atoms, which has the largest first ionization energy? So it's specifying the first ionization energy. So it's going to be something that's pretty content the way it is. So it's going to be kind of happy as is. All right. So which one of these things is it's going to be the hardest to remove an electron? Happy as is. It's also going to have the greatest electronegativity, generally speaking, which means it's going to be generally the smallest thing on there. So looking at these elements, hopefully it becomes clear that it should be choice D, sulfur, right? 14 is the same but different. Which ones has the lowest first ionization energy? So we're talking about something that'll be easy to remove one electron, right? So maybe something that's a metal. Metals like to lose electrons. And which one's going to be the most happy after losing one electron? It's going to be the one that has only one valence electron, right? So all those things are like 2, 8, 1. You get rid of that 1, it has 8. Or 2, 8, 8, 1, which I think is potassium, right? It'll be pretty happy it gets rid of 1 because it's going to have that stable octet. So the alkali metals are going to be the easiest ones to remove that first electron. 15. Which equation correctly represents the first ionization energy or first ionization of aluminum? So first ionization means we're starting with a neutral atom, right? Ionization is the process of removing an electron. So it'll become +1 and a separate electron. So which one of these things is it? The choice D, as in David. Right? Notice they are also all in gas, which is important because the definition of ionization energy is how much energy it takes to remove an electron in its gaseous phase. Oh, hey, wait, look. Right? B can't be right because of this negative charge there. A can't be right because we don't start with a neutral atom. C can't be right because you're gaining an electron, and that's electron affinity. And E can't be right because of that positive start, and it's gaining an electron, so it's like doubly wrong. All right, 16. Which of the following correctly represents a second ionization energy? All right, so if it's a second ionization energy, we already lost an electron, so we got to start with calcium +1, right? Ionization is removing an electron, so it's going to become even more positive, and it removed 1 electron. So which one of these is it? Choice B. All right. Choice A would be the right answer if they were asking for the first ionization energy, but they're not. All right. C is just wrong, right? It's just wrong. It's gaining an electron for D and E. Those aren't ionization energies at all. 17. Which of the following elements blank has the most negative electron affinity? All right. So that means it's going to give off the most energy. So it's going to probably become very stable. Afterwards, which one of these things become the most stable after it gains an electron? Well, it's going to be the thing that has 7 valence electrons, because then it'll become 8. It'll be a stable octet. That's going to be the best thing there. So, fluorine. Of the following elements, blank has the most negative electron affinity. So, remember, negative means it's a negative delta H. We're talking about losing energy, which is favored, right? So the most negative is going to be the most favored for gaining an electron. It's same thing but different for the last problem, all right? The thing with 7 valence electrons is going to become the most stable after it gains an electron. Chlorine, best option there. All right, you could also probably follow the trend, the pattern for electron affinity. 19. Which of the following correctly represents the electron affinity of bromine? All right, so you got to remember, well, it's kind of a definition question. What is electron affinity? And it is the gaining of an electron of an element in its gaseous phase, right? So if we're looking at 19 and we're looking at bromine, we got to look at just one atom, right? It's a Brinkelhoff, so these are going to throw you off probably. That's why they're there, trying to get you to mess up. But if we're looking at just electron affinity, we want to look at one atom gaining 1 electron in its gaseous phase. So it would have to be B. And 20. In general, as you go across the period in the periodic table from left to right, so we're going left to right, the atomic radius, well, we talked about that earlier, should get smaller because the effective nuclear charge is going up. Electron affinity becomes more increasingly negative, right? because it's becoming more and more of a favorable thing to gain one electron. And first ionization energy should go up. It should become even more difficult to remove one of those electrons. So looking at 20, best choice would be D, decreases, increasingly, negative, and increases. All right, well, that covers the trends. I hope you found the video helpful, and I'll see you in class.